Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with session number 55, first year Neet. In the last session, we have started laws of motion and we have discussed concept of force, first law of motion, change in momentum. All these details were discussed. So let us continue with today's discussion. Today we'll start with Newton's second law of motion. Okay. So this is the statement. The rate of change of momentum of a body is directly proportional to the resultant or net external force acting on the body, and it takes place along the direction of force. So rate of change of momentum is directly proportional to net external force acting on the body. And this rate of change of momentum direction will be along the direction of force, isn't it? So mathematically, this is how it can be expressed. F net is directly proportional to dp bar by dt. If we introduce a constant of proportionality, this can be expressed further as F net is equal to k into dp by dt, where k is constant of proportionality. Okay. So this is further how F net can be written. F net is equal to k into d by dt of mv. In the last session, we have discussed linear momentum. Linear momentum p bar is, it can be expressed as m into v bar, isn't it? So further, since m is a scalar, okay, if m is constant, that m can be brought outside, and you can write this as dv bar by dt, m into dv bar by dt. And what this dv bar by dt? It's nothing but acceleration. It is nothing but acceleration. Rate of change of velocity is nothing but acceleration. So finally, this is what equation we are left with. F net is equal to k m a bar. Okay. So finally, this is how it can be concluded. So what has happened to this k? Listen, children, whatever constant of proportionalities we see in physics, in any relation, if some physical quantity is proportional to some other physical quantity, there you can write constant of proportionality, and the value of constant of proportionality can be obtained with the help of experiments. Okay, we have to do some, experiment, and in that experiment, whatever data we will extract, in that data we will be able to identify the constant of proportionality. And here the constant of proportionality from the experimental observations, it comes out to be as 1. So if k is replaced with 1, finally what will be your equation? F bar is equal to ma bar. So this is how mathematically you can express Newton's second law of motion. When it comes to the question of, how the statement of second law of motion can be expressed mathematically, in two ways you can express. In this way you can express F net is equal to k. Anyways, we have come to know that k is 1. So F net equal to, directly you can write dp bar by dt, or you can also write like this, F net is equal to ma bar. This is the equation with which most of you are familiar, even at your school level, isn't it? But like this also you can express F net is equal to k, replace with 1. So F net can be directly written as a dp bar by dt, or F net can be written as ma bar. So whatever force term you see in Newton's second law of motion mathematical equation, that force is not just force, it is net force. It is net force. What does it mean? If net force acting on a body is 0, it means ma is equal to 0. ma is 0 in the sense, a is 0, because m cannot be 0. Every body possesses some non-zero value of mass, isn't it? So a will be 0. A is 0 in the sense, what does it mean? There is no any acceleration. There is no any acceleration in the sense there is no any change in the velocity. It means the velocity is constant. It means if a body is acted upon by a net force equal to 0, okay, either it stays at rest position, it might be at rest position, or it might be maintaining a uniform motion, a uniform velocity. Okay. Now let us have a look at this one. In this equation, since m is constant, it was brought outside. What if m is a variable and v is constant? We can write like this only when mass is constant. What if mass is varying? What if mass changes and velocity remains constant? In that case, what you can do is, in this equation, instead of bringing m outside, you can bring v outside. So F net is equal to v bar into dm by dt. So this dm by dt is what? Rate of change of mass. So this is how this Newton's second law of motion mathematical equation can be expressed if velocity is constant and mass is changing with the time. Okay. So we'll discuss about this particular equation. There are a few applications connected with this one. Okay, so these are a few details connected with Newton's second law. Okay, so anyways, force. I told you in dynamics we really concern much about the cause for the motion. What is the cause for the motion? Force acting on the body is the cause for the motion, isn't it? So in this equation, with the help of this equation, we can actually find out net force acting on the body, isn't it? Right? So let us further see this one. A metallic plate of mass m is kept held in mid-air by firing n bullets in t seconds, each of mass m with a velocity v from below. So this is one small application connected with Newton's second law of motion. So what was the situation he is describing? A metallic plate of mass m is kept held in midair. So it is in midair. It is not moving. How is it possible? It is possible because he is firing n bullets in t seconds, each of mass m with a velocity v from the below. From the bottom, he is firing the bullets. So each bullet is coming and it is striking the plate. So whatever plate's velocity is there, it is balanced by the force imparted to the plate by the bullets. Okay. So here, this is the plate, let us say. With this gun, let us say bullets are fired. Okay, bullets are striking the plate here. Now bullets weight will act in the downward direction, which is equal to mg, and the force due to striking bullets f net, it will be in the upward direction, isn't it? So now let us find out. F net is equal to what? Change in momentum by time. Here time is given as t seconds, right? So change in momentum can be expressed as final momentum minus initial momentum, isn't it? So final momentum is this one, minus nmvf minus nmvi. That's how you can write final momentum, because here the bullets, they are not passing through the plate. Anyways, they have to fall back, or they have to rebound, or they may fall dead. They may fall dead in the sense of what, after striking against the plate, they will lose their entire velocity, and with a velocity equal to zero velocity, they will fall down like freely falling body. Okay, so these two cases are possible, and since the direction is in the downward direction, in the opposite direction, here you will have minus nmvf minus nmvi. Vi is initial velocity, vf is final velocity. And here we are talking about first possible case. If the bullets are falling dead, in the sense, after striking the plate, bullets velocity is becoming zero. So final velocity is zero. Final velocity is zero in the sense this term vanishes, and you will be left with only nmvi by t minus nmvi by t. If you consider only magnitude, the net force acting on the plate will be equal to nmv by t. That's how you can write. If the bullets are rebounding with the same velocity, then what happens? This equation will be written here, and this is what you will get. Finally, F net is equal to 2 nmv by t. And if a plate is, it is held in midair, what does it mean? Whatever this mg is there, that mg is exactly equal to this F net. So in the case if bullets are falling dead, you can equate this nmv by t to mg. If bullets are rebounding with the same velocity, this 2 nmv by t can be equated to mg, and you can solve corresponding problems. Okay, so that's how this this application can be handled, and we will deal with the further applications. Okay, so let us see. Now let us talk about applications of variable mass. Okay, so here I'll start with the machine gun model. Machine gun model, what happens if you keep on shooting the bullets with a machine gun? Continuously some force will be acting on our shoulder, isn't it? So unless we exert the same amount of force back on the gun, we cannot hold the gun firmly. Okay, it won't be stable, and we'll be missing the aim. We cannot shoot the target. Okay, so let us try to find out how much of force the soldier has to exert on the machine gun to hold it firmly. Okay, it will be equal to what? It will be equal to force exerted by bullets which are fired on the shoulder. So let us find out one by one. So I'll assume that let mass of each bullet is equal to m, and velocity of each bullet is equal to v. Let n bullets are fired in a time So these are the details I am assuming here. So let us find out the force exerted on the shoulder because of ejection of the bullets. This can be written as, according to Newton's second law of motion, F is equal to change in momentum by time. Here time, interval it is taken as t. Okay, so this dp I will write it as final momentum minus initial momentum by t. Okay, final momentum, see, it is equal to how many bullets are shot in a time t, n. So n number of bullets, momentum will be equal to n mv minus initial momentum, it's 0. When the bullets are inside the gun, they are at rest position, so initial momentum is 0. So finally, what did you get? N mv by t. Nmv by t. So the force the soldier should exert on the gun to hold the gun firmly is Nmv by t. This is quite similar to the previous case where we have discussed about holding a plate in still position in air, in mid-air by shooting bullets. If bullets are falling dead, this is what we have got. Okay, force exerted by the bullets which are falling dead is equal to Nmv by t, and this was equated to weight of the plate, isn't it? So let us discuss about one more case. Here I'll take a water pipe, okay, and I'll make sure that water coming out of the pipe will strike the wall horizontally. Let us say here there is a wall, okay, and here let us assume that here there is a pipe. I will increase the size here. Okay, from this pipe, let us say water is coming out and it is striking the wall like that. If at all, if wall is moved away, what happens? It follows a parabolic path, like a horizontal projectile kind of trajectory. So here I'll assume that the pipe is okay, it's close to the wall such that the whatever channel water jet is there, it is perfectly in cylindrical shape. Let area of this water, whatever water jet which is in cylindrical shape is there, I will assume its area as A. Okay, I will assume its area as A. Let us try to explore various possible cases. Here it may be possible that water after striking the wall, it may fall down. Water after striking the wall, it may rebound, okay, with the same velocity, or it may rebound with a different velocity. Okay, or not only like this horizontally, not only along along horizontal direction, you can also orient this pipe along this direction, and water jet strikes the wall at some angle with the horizontal or with the vertical. Okay, these things they sound quite similar to change in momentum cases. Okay, in the previous session we have discussed about change in momentum, where one ball is projected towards the wall. What if that ball is falling dead? What will be the change in momentum? Okay, here we need to find out change in momentum, otherwise we cannot find out how much force is acting on the wall, isn't it? Because force is equal to change in momentum by time, isn't it? So here change in momentum is a very important parameter that we have to find out. So in case of a ball, let me recollect very briefly. If a ball is taken like this, let us say a ball of mass m is traveling towards the wall with a velocity equal to v, and after striking, if it falls dead, change in momentum. What did we write expression for change in momentum? It was written as simply mv. The magnitude of change in momentum is written as mv. What if the ball is rebouncing with the same velocity? Ball is rebouncing with the same velocity. In this case, change in momentum was written as 2mv. 2mv. I hope you remember all these points. What if the ball is rebounding with a different velocity? If it is rebounding with a different velocity, in that case, change in momentum is expressed as m of what? v1 plus v2. Let us say with a velocity v1 it is striking the ball, with a velocity v2 it is bouncing. Okay, what if it is striking at some angle with the wall? Okay, here the change in momentum is expressed as 2mv cos theta. 2mv cos theta. Cos theta, if the initial velocity direction is making an angle theta with the horizontal. If the theta is angle made with the wall, in place of cos theta you will have sin theta. So these are changes in momentums that we have already explored in the previous sessions. We need this data to understand this water jet case, I will write all these details separately. Okay, change in momentum in case of if the ball is falling dead. In that case, the change in momentum is what? Delta P is equal to m into v. If it is rebounding with the same velocity, change in momentum is expressed as 2mv, isn't it? If it is rebounding with a different velocity, change in momentum is equal to m into v1 plus v2. Okay, if you are making sure that the ball is striking the wall at some angle theta with the horizontal, in that case change in momentum is 2mv cos theta. If this angle theta is made with the wall, in that case change in momentum is 2mv sin theta. That's how you can write. Okay, so let me erase this and I'll discuss various other cases connected with this one. Okay, so I'll correlate this one with the data, already available data. First case is, let the water jet is falling dead after striking the wall. So it is falling dead. It is falling dead. In that case, how much force will act on the wall? Let us find out. So force is equal to change in momentum by time. Change in momentum by time. Let velocity of this water jet is equal to v. Velocity of this water jet is equal to v. I will assume it like that. So change in momentum in case of if the matter is falling dead, what is that? Change in momentum is equal to mv. So simply I will write here mv by t. Okay, let us say density of water is d. D is what? Density. Here not only water, you can take any other liquid also, no problem. Okay, so density I am assuming it as d. Mass can be expressed in terms of density as density into what? Volume into v. Okay, density is equal to mass by volume, mass is equal to density into volume. This volume can be written as cross section area multiplied with the length into v. Whatever cylindrical imaginary surface is there here, it's not imaginary, in fact that is actually a channel in the shape of cylinder. Okay, so let us say length of that one is equal to L. Therefore volume of this liquid is equal to A into L divided by T. Okay, so now L by T is what? L by T is nothing but like a distance by time. Distance by time. Distance by time is nothing but velocity. So what you will have finally, dA, in place of L by T you can write velocity into velocity. So dA v square. So this is what force acting on the wall if the water is falling dead. If the water is falling dead. So let us consider the other situation. What if water is rebounding with the same velocity? If it is rebounding with the same velocity, let us see what equation we will get for force acting on the wall. Let the water jet is rebounding with the same velocity. If this is the situation, again force expression is what? Change in momentum by time. Change in momentum in case of rebounding with the same velocity is what? 2mv by t. Mass can be written as density into volume. Volume can be written as area into length into v by t. L by t is what? Velocity. Velocity into velocity, v square. So 2 into density into area into v square. So this is the force acting on the wall. Okay. What if it is rebounding with a different velocity? If it is rebounding with a different velocity, I will conclude here itself. Here itself. Okay. What you can write here in place of change in momentum? M into v1 plus v2 by t. This mass can be written as density into volume. Volume is area into length into v1 plus v2 by t. Or this can be written as dA L by t, initial velocity. Okay, whatever velocity with which it is striking the wall, v1 into v1 plus v2. If both are same, you will have 2v1 and again 2 dA v1 square you can obtain. So similarly, in these two cases also, what you can do is you can say replace this delta p with change in momentum. Okay, so that's how change in momentum connected with this water jet can be handled. Okay, so let me talk about the one more small case connected with this variable mass. Conveyor belt. Let a conveyor belt is moving with a constant velocity. If it is moving with a constant velocity, what is the extra force required to maintain that constant velocity if mass is changing with the time? Okay, on conveyor belt, variable mass will be dumped all the time. For example, in stone crushers also, stone will be crushed and small pieces of stones, they will fall on the conveyor belt, and conveyor belt will be traveling like that, and those stones will fall somewhere. There will be a heap. Okay, so the amount of the quantity of stones, the matter falling on the conveyor belt, it varies from time to time. Okay, but the conveyor belt maintains the same velocity. It means always the machine has to create an extra force to make sure that the conveyor belt maintains same constant velocity. So in this case, force expression can be written like this: F is equal to V into dm by dt. This is from Newton's second law of motion. F is equal to dp by dt. P is written as mv. V is the constant. It was brought outside. So you are having dm by dt. What is this? This is rate at which mass is added to the belt, to the conveyor belt. Okay, and this is constant velocity maintained by the belt. Okay, so this is the extra force required to make sure that the belt is maintaining constant velocity. Okay, students. So this is what we can talk about under the heading of applications of variable mass. Okay. Now let us discuss about this problem. A machine gun fires a bullet of mass 40 gram with a velocity 1200 meter per second. The man holding it can exert a maximum force of 144 newtons. Here the human being's capacity is given. The man can exert only a maximum of 144. It means the number of bullets he can shoot in a given time interval are limited, isn't it? Once again, how many bullets can he fire per second at the most? So maximum how many bullets he can fire in a second. So let us solve this one. Just now we have seen this machine gun model. Force force that the person has to exert is equal to what? N mv by t, where n is the number of bullets that the person can fire, and the t is what? Time in which these bullets are fired. M is mass of the bullet, v is velocity of the bullet. Here we don't know what n is, and t is given, it's 1 second. Okay, in a second, how many bullets can he fire per second? Okay, so in 1 second, how many bullets he can fire? That's what he is asking for. Okay, so time is 1 second, and mass is given as 40 grams, or this can be written as 40 into 10 power minus 3 kg, and velocity is given as 1200 meters per second. So let us find out n. So from this equation, n can be written as ft by mv. F is how much? Maximum he can exert a force equal to 144 newtons. So I will replace this F with 144 into time 1 second divided by mass of the bullet 40 into 10 power minus 3 kg, 10 power minus 3 into velocity 1200 meter per second. So 1000 into 10 power minus 3. 4 12s are 48. 144 by 48. It's 3. So n is equal to 3. So maximum how many bullets he can fire in 1 second? 3 bullets. Okay. So that's how you are supposed to solve. Let us try one more question. One more small question connected with variable mass. A truck of mass 500 kg is moving with a constant speed 10 meter per second. If sand is dropped in the truck at the constant rate of 10 kg per minute, so at what rate the mass is dumped, the sand is dumped into the truck 10 kg per minute. In each 60 seconds of time, 10 kg of mass is falling into the truck. The force required to maintain the motion with constant velocity. So whatever velocity it is maintaining 10 meter per second, if it is supposed to maintain the same velocity, how much force, how much extra force the truck engine has to generate, okay, to maintain constant velocity. So that's what we have to find out. And this 500 kg mass has nothing to do in the present situation. Okay, so here all that we need to worry about is rate of change of mass that is being added into the truck. Okay, so already we have dealt with this model. The extra force required is expressed as constant velocity multiplied with dm by dt, isn't it? And this is what he is asking for. And velocity, what is the constant velocity of the truck? 10 meter per second. And the dm by dt is given as 10 kg per minute. Per minute. In a minute, how many seconds will be there? 60 seconds, right? So what you will have 1 by 6 kg per second. So this is a dm by dt value. Let us find out f. F is equal to v 10 into 1 by 6. 5 by 3 or 1.67 newtons. So this is the extra force the truck has to exert. Okay, so truck engine has to exert so that it can maintain a constant velocity of 10 meter per second. Okay, so let us try one more question. So let us try this question as well. The momentum of a body in two perpendicular directions at any time t are given by px. Might be this momentum is along x direction, is given as 2t square plus 6. So momentum is a time function of time. What does it mean? It means momentum is changing with the time. If you replace this t with the various numbers like time t is equal to 1 second, time t is equal to 3 seconds, momentum will be different. It means momentum is changing with the time along x direction. Similarly, along y direction also momentum is changing with the time. Okay, so py is expressed as 3t square by 2 plus 3. Px is expressed as 2t square plus 6. The force acting on the body at t is equal to 2 seconds. We all know that force acting on a body can be expressed as rate of change of momentum dp by dt according to Newton's second law of motion. So first what we have to do is we'll find out how much force is acting along x direction and along y direction. Since these two forces will be mutually perpendicular to each other, it was said like that. See, the forces acting here, see, a body in two perpendicular, the momentum of a body in two perpendicular directions. So here whatever forces you will be calculating, you will be finding corresponding to this px, corresponding to this py, both will be mutually perpendicular. So we can find out resultant force. Okay, so let us try to solve this. Since F is equal to dp by dt according to Newton's second law of motion, so Fx, force along x direction, can be written as dpx by dt, d by dt of what is px? 2t square plus 6. It's a number. So d by dt of 6 is 0. D by dt of t square is 2t. 2 into 2t is how much? 40. So what is fx? Fx is equal to 40. Okay. Similarly, fy. Let us find out fy. Fy is equal to dpy by dt. D by dt of what is py? 3t square by 2 plus 3. Okay. D by dt of 3 is 0. Isn't it? D by dt of 2t square is what? 2t. 2 gets cancelled. You will have 3 into t. Isn't it? 3t. So Fy is equal to 3t. So therefore, x component of force, y component of forces are known to us. Can't we find the net value of force? Yes, of course. Net value of force F is equal to under root Fx square plus Fy square under root Fx square 4t square. It's 16t square plus Fy square 3t square 9t square. 16t square plus 9t square, it's equal to 25t square, isn't it? So F is equal to 25t square under root, or this can be written as 25, you can write this as 5t, isn't it? And he is asking about the force acting on the body at a time t equal to 2 seconds. So now replace the t with 2 seconds. So F at t equal to 2 seconds is 5 into 2, 10 newtons. So how much force is acting on the body? 10 newtons of force is acting on the body. Okay, students. Thank you. With this, I will close the session and we'll continue our discussion in the next session connected with the laws of motion. Thank you, students.